All right, well, I'm going to get started at 1 o'clock. Had to open up some notes there. But in terms of what we're doing, we're getting very, very close to the end, right? We have 2 more days of material in here. And then, like I said last class period, I think I said this last class period, the finals week is a week that we will not meet in the classroom, all right? Normally, on finals week, if I had in-seat tests, I just take the in-seat test on finals week, that first day of finals week. But because our tests are online, that means we will plan on not meeting finals week. I will be around if you need help with anything. So during this time, I'll be probably in my office on finals week. But as far as actually meeting in the classroom, I plan to have all of the material done by Thursday this week, and then finals week we won't meet in the classroom. Is that right? All right. So we were dealing with regression last time, and the idea was we're going to look at a scatter plot and we're going to decide what type of function it looks like. So let me fast forward to the scatter plots. Oh, it's a little bit delayed. Why that is. So we look at this one, and you see that the growth is not always steady, but rather as you go to the right, the growth sort of increases. And so that was an indication that this was an exponential function. Or, in other words, that an exponential function will fit this the best. We looked at the beers and the blood alcohol content, and we said, well, this one, the growth is pretty steady as I go left to right. Since we have pretty steady growth, that's probably a linear function. All right. Obviously, it doesn't look like a perfect line. It's not generally going to. We looked at this one, and that had that classical shape where on the left we go down, and then we go back up after we reach 2. 2 is our lowest point. So we have that classical parabolic shape, which is a quadratic indicator. All right. And then we said there are situations in which there's no pattern available. Like this one. If you look at these data and you say, well, what does this look like? You'd say, well, it doesn't look like a line, doesn't look like an exponential function, doesn't look like, excuse me, it doesn't look like a rational function, doesn't look like a quadratic function. So there's really no pattern here. And that is going to be one of the possibilities. So one of the possibilities is these doesn't really look like anything we've seen, or doesn't look like there's a pattern at all. Okay. So once we recognize those types of functions, now we go on to actually creating the regression models. Okay. So essentially, once I identify what type of function it is or what situation, then I'm going to turn to some technology to build the model that best fits the data. All right. And you can do this by hand, but it just takes extremely, it takes an extreme amount of calculations. So it would take a long time if you had to do this by hand. That's why we almost always just utilize technology to get it for us. Okay. Now, because it takes some computing power, a lot of times once we get into like the test and the homework, you won't have necessarily access to the same computer programs that I'm doing. I'm going to use Excel when I do this, but when you're taking the test, you might not have access to Excel. So I probably won't ask you to create the model using Excel. I'll just say, here's the model Excel gave. Does that make sense? All right. And this model is going to be called the regression model. We'll talk about what that model is in a second. Now, the regression model is going to have its limitations. We're going to ask the computer to create, or the software, to create the best model it can, given what we tell it to. So if we say, create an exponential model that fits the given data, that fits the given scatter plot, well, if an exponential model is not going to be a good one, it's still going to create an exponential model, just might not be very good. Does that make sense? So the computer, the software, gonna create the best model it can. That doesn't mean that model is very good. So with every regression model, there's going to come a measurement with the model called the correlation coefficient. The correlation coefficient, it tells you how well the model fits the given data. All right. So it's some measurement of how well the model matches up with the data. Now, the models we're going to be building will all have a correlation factor, which they call R squared. Okay, there's other correlations. If you build a linear model, there's something called a Pearson correlation coefficient, and that's a lowercase r. But the models we're going to look at, sometimes they'll be linear, sometimes they'll be exponential, sometimes they'll be quadratic. So all of those will have an R squared. And essentially, R squared is going to be between 0 and 1. The closer it is to 1, the better the model fits the data. The closer it is to 0, the worse the model fits the data. So 1 is better, 0 is worse. Okay. Everybody follow that? And we'll talk about sort of where the cutoffs are and all that kind of stuff in a few. But I just want to draw your attention to this correlation coefficient now because you'll see it when I create these models through Excel. All right, so let's look at this data set. I'm going to show you how to use Excel to find the regression. All right. Now, if you remember, this data set was associated with this scatter plot, right? And that scatter plot, we said, looked exponential. That was our last class period. So we want to create an exponential model for this data set. So let me go ahead and put this data set into Excel. You can just watch how I'm doing this. So I go to Excel. Yeah. And I put those data in. Now I'm going to highlight these, and I am going to insert a scatter plot. All right. So you go to insert, and then over here in all the graph drawings, there's a scatter plot chart. So we're going to insert a scatter plot. Try to make that a little bit bigger so people can see it. That work? All right, now we want this scatter plot. We want these data to generate out an exponential function. So what we do is you just right click on it, and then you can hit this plus sign. All right. If you go down to the phrase trend line, you can click this little arrow, and you can get a linear, an exponential trend line, or you can just click on more options. I'll click on the more options right now. You can always click on more options. So if I want an exponential trend line, when it says trend line, it just means the regression. So I just click on the exponential. I said we wanted exponential here. And then down here at the bottom, it says display equation on chart and display R squared value on the chart. So I'll just click on both of those. Hopefully I can. We'll make that bigger. Try to make that a little bit bigger. Put 9 right now. I'll make it 24. There you go. So notice how I just had Excel make me an exponential function. Now the exponential function it made is y equals (1.1796) e to the 0.0805 times x. And it gave me an R squared of 0.9738. Notice 0.97, that's pretty close to 1, right? I said the closer it is to 1, the better the fit. And you can see this fits pretty well. Like this line is pretty close to these points. If I get that. So when we say better fit, we just mean the line's closer to the actual data points. Does that work? So that's it. It's a few clicks away. And once again, you just hit the plus sign if you want to do this on your own. You go to trend line, click this arrow. I always like going to the more options because then you can pick out anything you want. Display the equation, all that kind of good stuff. Oh, we had a trend line. I didn't want to do that. That would be the linear line. Obviously, that doesn't fit as well, does it? All right. Let me get that out. There we go. Okay, got it off. Does that work? So that's the whole thing. That's basically it. So that's the model. We have correlation that R squared gives me the correlation of 0.9738. Okay. Now, the whole goal of having this model is to be able to do prediction type stuff. What would we predict the US debt to be in the year 2020? What would this model predict the US debt to be in 2030? Now, before I actually answer those questions, I want to remind us that the X values, that the values here were years since 1980. So 0 stands for 1980, 5 stands for 1985. So if we want the year 2020 and we want the year 2030, then we have to make sure we understand, oh yeah, that T is since the X is since 1980. Does that make sense? So predict debt since 1980, or did I say that? Dang it. Predict debt for 2020, and T measures the years, or X, in this case I used X. That's generally what Excel always gives me, is X's and Y's. So since we're talking about years since 1980, if you go from 2020 down to 1980, that's 40 years. Does that make sense? All right. So all you do is you take this model. Y stands for the debt. And all I have to do is plug that in to my calculator. We've dealt with exponential models of base E before, so it should be fairly straightforward. And I'm just plugging it into my calculator. I get a debt of approximately, I'll round this to two spaces, 29.52. By the way, that's in billions of dollars. Or billions or trillions? Can't remember. It should be, actually, I think it is a typo. It should be trillions of dollars. Is that okay? Now that I'm remembering, I'm pretty sure it should be in trillions. And where would this predict the debt for 2030? Well, that's another 10 years. So X now is 50. And I would plug in $50 into that X value. Once again, just type that in my calculator. And it ends up, again, I'll round this to 2 decimal places, at about 66.03 trillion dollars. $66.03 trillion. Okay. Now, obviously, 2020 is already past us, so you could go and see how well this model actually matched up in 2020. Okay. We're not in 2030 yet, but you could see how well the debt was in 2020. In fact, let's see how well this model predicted the debt in 2020. U.S. debt. Debt in 2020. All right, it looks like in 2020 where the national debt was about 27, close to 26. Oh, I'm sorry. I thought I was, sorry about that. Looks like national debt in 2020, probably at the start of the year, was about 26.945 billion, which is 26.945 trillion. And in 2021, it was about 28.428. So our model wasn't perfect, but it gives you a pretty good rough estimate, doesn't it? Gave us a pretty good rough estimate, even though it's not perfect. Okay. And there's probably people who have slightly different numbers. Yeah, here it says 26.9 trillion. So not too far off of what we were imagining. Any questions about that? About those ideas? All right, well, let's do this next one then. We're gonna do the number of beers individuals drank and their blood alcohol content 2 hours later. All right. So once again, if we want to create the regression model, first thing to do. Uh-oh, can I copy and paste that? Is that a picture? Uh-oh. Let me look. It's on this one, I know that. If I can, yeah. So I'm going to copy all these data. Go to Excel. I'm going to create a new sheet. Number of beers, blood alcohol content. There you go. Goodness, keeps getting cut off. There we go. So then I go and highlight those data. Highlight those, make sure those are highlighted. And then we're going to insert our scatter plot. Make that a little bit bigger so it's easier to see. And then I hit this plus symbol. If you don't see the plus symbol, just right click on it. Right click on the chart. Hit the plus symbol, trend line. And then I like to always go to more options. Even though I see the linear option right there, I'm going to go to the more options. Now, the reason I said linear is because in the last class period, we looked at this scatter plot. We said it looks mostly linear. And so I'm going to click on the linear, and I'm going to ask it to display the equation and also to display the R squared. I'll move that over here. Try to make those things a little bit bigger, easier to see. There you go. There's our linear equation. Y equals 0.0143 times X minus 0.0008. I'll try to do this in blue. And then with an R squared of 0.8206. Now 0.8206 is still fairly close to 1. All right. So it's still a pretty good R value, but it's not quite as good as our last one. Okay, so that's it. We asked technology to give us, and technology gave us the model. Okay. So we've seen how Excel can give us that. We got that model with that R squared. Oh, hit the wrong button. And now what we'll say is this. Let's use that model to predict the blood alcohol level of a person who has had 2.5 beers. Let's use the model to predict the blood alcohol level if a person had 4 beers. So let me write that down. Predict blood alcohol level. And we've had 2.5 beers. Predict blood alcohol level if they had 4 beers. And just like before, just like in the algebraic case, all we're doing is figuring out which one is the X, which one is the Y. X was number of beers, Y was the blood alcohol level. So I just plug in 2.5 in for the X. Calculate that. And then for this one, I'll just plug in 4 for the X. Calculate that. On this top one, I get a Y of 0.03495. That's the blood alcohol level prediction. All right. And then on the second one, I get 0.0564 as the blood alcohol prediction. Right, that. So the data generated out this model, and now once I have this model, I use it just like I use the algebraic models from last chapter. I just plug in values, see what they are. Now we do have to understand, because of how I'm generating out this model, the X value here stood for the number of beers, and the Y value stood for the blood alcohol level. So we do have to, be aware of what variable stands for what. But other than that, I hope that's fairly straightforward. Did everybody understand why the X value is that way and why the Y value is that way? The reason for the X value being associated with the number of beers is because that was my first column. And my second column was the blood alcohol level or blood alcohol content. So that was what Excel automatically calls the Y. It automatically calls the first column the X's and the second column the Y's. And in our last example, when we were doing years since 1980 and US debt, I should say in trillions, not billions. Since the years since 1980, since those are my X value, those got graphed on the X-axis. And the trillions of dollars in debt got graphed on the Y-axis. Is that right? Same thing here. Number of beers got graphed on the X-axis. Blood alcohol level got graphed on the Y-axis. All right. So number of beers was the X. Blood alcohol level was the Y. Okay. Let's do a new one that we haven't looked at yet. And let's do this from the beginning. So let's say we are looking at the 2 pieces of data I have here. Now the 2 pieces of data are the number of McDonald's restaurants per million people in those various countries. And the other is the happiness level as reported by surveys of people in those countries. All right. So let's try to create a model with these data from the start. You okay with that? So I'm gonna go take these data and I'm gonna put those into Excel. There we go. And then just like we did before, let's take those data, insert, scatter plot. Oh, you know what? I don't want to do it that way. Since I have this extra line of which country it came from, I don't want to deal with that. Let's just create a scatter plot for those two columns. So just highlight those two columns. There we go. Create a scatter plot of here. And because the McDonald's per million came first, that becomes my X, and happiness level becomes my Y. Everybody get that? Now, what's that look like? Does that look linear? Does that look exponential? Does that look quadratic? Or does that look rational? Well, it has this arch that goes up and then kind of comes back down, doesn't it? That's a good indicator of that quadratic. Remember that parabolic shape. So we go up, then we go down. If you want a quadratic equation, it's a polynomial of degree 2. So when you go and ask to find the trend line, you're going to hit more options. And you don't want to be on linear, you want to be on a polynomial of degree 2. I follow that. So it's not going to say quadratic. You'd have to pick polynomial order 2. And then once again, we'll display the equation, display the R squared, and that's it. Move that thing around. There. Make it a little bit bigger. There you go. So now we have a quadratic equation for these data. And notice that the R squared is about 0.8909. It's a pretty ugly quadratic equation, though, isn't it? It's hard. Ugly is in terms of we get ugly coefficients. All right. But not real tough to deal with. Pretty easy to deal with, in fact. So here's our scatter plot. Those are the equations that Excel gives me. And then if we wanted to use this to predict, we can go right ahead and do that. Predict the happiness level if a country has 4.45 McDonald's per million people. Predict the happiness level if a country has 1.84 McDonald's per million people. And all we have to do is go back to this equation, y equals negative 2.699x squared plus 23.231x minus 12.967. And realize that the McDonald's per million, those were the x's. Happiness level is the y's. So all I have to do is plug in 4.45 into the x's to make my first prediction. Let me go ahead and do that. So everywhere you see an X, for the first prediction, plug in 4.45. And then for the second prediction, you're going to plug in 1.84 everywhere you see an X. And other than getting numbers that have been rounded to like 3 decimal places here, it's the exact same type of predictions we're making everywhere else. All right. So just type that in your calculator. In the first case, the happiness level is approximately 36.96. And in the second case, again, just have to type in all that stuff. Uh-oh, hit the wrong number. In the second case, I got a happiness level of approximately 20.64. Is that right? Again, this is self-reported happiness via some survey that they did with these in these countries. There we go. All right. So we've looked at the scatter plot. We've identified the function type. We used Excel to create the function. And then once we have the function, we can use it just like any other algebraic function we would have gotten in our, in our previous chapter. Okay. Once you have a function, you can go ahead and use it. What we're going to see in the next slide is two things: gun laws, stricter versus less strict gun laws, and then murder rates based on governmental data. Here it is. For this select group of states. So this is ranking on gun laws. And essentially, the higher laws are the stricter gun laws. The higher numbers mean stricter gun laws. So Idaho has less strict gun laws. Massachusetts has fairly strict gun laws. So they get the higher number. Idaho is pretty loose about their gun regulations, and they have the lower numbers. They got Idaho, Mississippi. Lower levels of gun laws. So let's go through it again. Let's go through this. I'm going to try to copy this into Excel. I always like doing this with technology, just makes everything so much easier, right? All right. Try to do this. Maybe I'll do it this way. 16 is good. All right. Then highlight the two columns. Let's ask it to give me a scatter plot. You see a pattern there? If I told you what function does that scatter plot look like? Does it look like a line where you can just draw one line through it? Not really. Does it look like a rational where one side we go down, the other side we kind of level off? Does it look like exponential where the rate of increase changes, or the rate of decrease changes? Not to me anyways. Doesn't look quadratic where it goes up and down or down and up. Well, not to me anyways. This one doesn't look to be a pattern, does it? Right? It looks almost like an X, this data. All right. But it doesn't seem to be that, doesn't look like there's a pattern there. Let's force it to give me a trend line. Now, I'm going to force the trend line to be linear. All right? Is that okay? If you wanted your trend line to be quadratic, you could do polynomial of order 2. If you wanted it to be exponential, you could do exponential. All right? Notice none of these are fitting very well to the data. They don't look like they fit very well at all to the data. Here's our exponential, here's our linear, here's our quadratic. Do a power, that doesn't work either. So I'm going to just choose linear for right now, because that's usually the easiest thing to deal with. If I asked to give me a linear equation with the r squared, I want you to notice that it gives me this equation, negative 0.0062x plus 5.3144, and the r squared is 0.0012. Notice that r squared is really close to 0, isn't it? So that's a bad fit. Remember, closer to 1 are the better fits, closer to 0 are the bad fits. This one's very close to 0, therefore, probably bad fit. And so if you do get this scattered type information, your calculator, this is what I was trying to get at the very beginning of class, your calculator is going to make up a relationship even if there's not one there. However, that correlation comes along with it and says, hey, this is not a very good relationship. This model doesn't fit our data very well at all. Does that make sense? So again, no pattern here really that is visible. It almost looks like there's an X with the data. But if I wanted to get a model from Excel, Excel will give me one. It'll just have a crappy correlation. It'll have a crappy R squared with it. That makes sense? There you go. 0.0012. Not very good. And when there doesn't look to be a pattern, the language that we use is we say those two variables, the X and the Y, are not correlated. If there are nice patterns, we say the two variables, X and Y, are correlated. So the years since 1980 and the debt, we would say are correlated. The number of beers someone drinks and their blood alcohol level are correlated. All right. Correlated means there looks like there's a pattern here. Not correlated means there doesn't look like there's a pattern. Right? No mathematical relationship that's any good exists in that scenario. Everybody okay with that? So that's how we create these things, creating those regression models. Now, since we've been making predictions, using our models to make predictions, I want to talk briefly about actually making those predictions. All right. When we were doing the algebraic modeling, and I said, and we asked, for instance, how much will be in the account after 10 years? We would get a pretty exact number. However, since our models in regression are based off of data, we always have to understand that our models will have some wiggle room when we make our predictions. All right? Like when we made the prediction about the debt in 2020 being right around 29 trillion. And then we looked it up and we said, well, it's actually closer to about 27 trillion. That's what I mean. The models will predict certain Y values, and there might be some wiggle room in there. Okay. Like I said, that R squared, that correlation tells us how well the model that we've created fits our data. If we have this special case of linear models, that correlation, it's actually the R, is called the Pearson correlation. Pearson's the last name of some guy. All right. So if it's linear, it's called Pearson correlation. And if you go into stats classes, they'll talk about Pearson correlation coefficients. That's all that is. But in all models, we'll have this R squared. In every model that we deal with in our class, we'll have an R squared with it. And like I said, closer to 1 is a better fit. Closer to 0 means a bad fit. Now, the R squared, or the line between a model fitting well and fitting poorly, can be drawn at almost any place you want. In the social sciences, oftentimes, if your R squared is pretty low, they'll still say it's a good fit. In our class, we're going to have to draw that line between good fit and bad fit at a certain place. So we're going to do it right in the middle. So if you draw a line segment from 0 to 1, the middle of that line segment is 0.5. In our class, we're going to say anything over here, anything between 0.5 and 1 is a good fit. And anything between 0 and 0.5, we'll consider that model a bad fit. Everybody right with that? But once again, this is for this class. This class, we're going to draw it at 0.5. If you go into other classes, they may move this down or up, depending on the context. A lot of times, social science experiments deal with really, really large sample sizes, and they'll move this down closer to 0. So they might get an R squared that's like 0.3 and still say it's a good fit. All right? In some of the hard sciences, they might want an R squared that's closer to 1. So they might have a 0.7, which is a bad fit. Does that make sense? In this class, because of the sizes of the data sets we're going to use, and just because of the nature of making it fairly easy cutoff, we're going to draw the line between good fit and bad fit at 0.5. So anything above 0.5 is a good fit, anything below 0.5 is a bad fit. If it lands perfectly on 0.5, we'll say that's a good fit too. Is that all right? So again, I want to just emphasize for the record, the 0.5 is for this class. And if you go into other classes, they might draw it at a different place. Okay? They might draw the change between good and bad fit at a different place. Okay? As we've already seen, the technology gives us the R squared. If we had to calculate this by hand, we could, but it's a big, long, complicated expression. Okay? Same thing with the regression lines. With the regression lines, we can calculate those by hand, but it's really, really long and complicated process. So it's much easier to deal with technology. And we've already seen, like in this example, in example 1 from last time, we had R squared of 0.9738. That meant that example 1 was a good fit. Right? We also did this prediction, these predictions already. We predicted the US debt in 2020 and we predicted the US debt in 2030. Since the R squared is pretty high, the R squared is 0.9738. That means it fits our model well. But also, since the R squared is pretty high, that means our predictions are probably going to be more accurate. They follow that? So R squared being high means the model fits the data well. But also, it means our predictions are going to be fairly close to being accurate. They're not going to be 100% accurate, right? 100% would be like a perfect 1.00. But they're going to be off by a little bit, like we saw earlier. We predicted the debt to be $29.52 trillion, and it was actually almost $27 trillion. Could be a little bit off, but not crazy off. When we did this example with the number of beers, we had R squared of 0.8206. That was a pretty good fit, right? For our purposes, R squared of 0.8206 lands in the good fit section. So this model fits our data pretty well. And we predicted the blood alcohol level if a person had 2 beers and waited a couple hours. What would their blood alcohol level be? We did that with 4 beers as well. Okay. And a 0.8206 means the model fits our data pretty well. And it means our predictions are going to be pretty good. Now remember, let me just write this down. We had an R squared of 0.82, oh, is it 8206? All right. No, I can't remember. I just had it on the screen. Yeah, 8206. Yep. That means we have a good fit. When we did our predictions, we predicted the blood alcohol level after having 4 beers in 2 hours. We said if we have 4 beers, you can look back at your notes, the blood alcohol level will be approximately 0.0564. Okay. When you're making these predictions, though, remember there's a little bit of wiggle room. This is not a perfect fit. So if you had 4 beers and then waited 2 hours, don't imagine your blood alcohol level is going to be exactly 0.0564. There could be off by a little bit, right? And if it's higher than this by a few points, you may be over the legal limit. Right? 0.08 is the legal limit, right? Drinking and driving. 0.08, I believe, is the legal limit. So don't say, well, this model says it's going to be 0.0564, therefore I can do this. Hopefully we all know that, you know, whatever the type of beer it is, the type of alcohol it is, and the individual person, based on those two things, it might be different from this number. Might be a few decimal points up or a few decimal points below. And a couple of hundredths makes a big difference legally between getting a ticket and not getting a ticket. Does that make sense? So, yes, it is a good fit, but we have to understand there's still wiggle room here when you make your predictions. Okay, okay with that? So, we'll go there. Okay. All right. Now, the gun laws data, when we did a model for these data, remember what we got for our R squared. Our R squared was 0.0012. That's a really bad fit, right? That's a really bad fit. It's like almost 0. That means the model that we created doesn't fit our data well at all. And that means if we use that model to make predictions, those predictions would be practically worthless, right? Because of that 0.0012 as our R squared. That makes sense? So 0.0012, not a very good R squared. Okay. Now let's do one more from scratch. Here we have an X variable and a Y variable. Oh, gotta go enable editing. So let's go to Excel. Insert scatter plot. What do you think that looks like? Mostly. Well, is there an increase as over time in the rate of change? That looks about the same steady rate of change all the time, doesn't it? Kind of going up the whole time. So I would say that's probably a linear. Go to the trend line. By the way, if you're ever on the trend line, you're like, oh crap, I don't have what Jordan has. It's this one, this little bars one that you hit. And that allows you to pick which trend line. So we're going to pick the linear, display, the equation, make everything a little bit bigger. Readable. So there we go. We get, oh, that moved on me. Sorry. We get an R squared, which is 0.9875. That's a really good R squared, isn't it? So you see how the line fits the data pretty well, but there is a little bit of wiggle room, right? Whenever you're doing these, there's a little bit of wiggle room. Your data points could end up off the line by a little bit. But the higher the R squared, the closer these data points are going to match this line. Bear up with that. So this is an R squared of 0.9875. That means it's a really good fit. And to answer the question that we're asked, what's this say about the equation? Well, it fits really well to the data. The equation fits really well to the data. And if we were going to use this equation to make predictions, they'd probably be fairly accurate. Okay? The higher the R squared, the more accurate we expect our predictions to be. Let's do one more. This is one we saw earlier. All right. So let's insert scatter. So a scatter plot look like this. We can already guess what's going to happen, can't we? If we put any type of trend line, not going to fit really well. Let's do an exponential one this time. Is that all right? So we'll do an exponential one this time. As you can see, if we do an exponential one, I get an R squared of 0.0522, 0.05. That's a really low R squared, isn't it? Okay. By the way, just so we're all on the same page, if we asked for a linear trend line, the linear trend line is not going to have the same R squared number as the exponential trend line. Everybody see that? It's 0.0397. Now, neither of these are very good. Okay? Neither of these are very good, but I just wanted to point that out. That the R squared, maybe an exponential might fit just slightly better than a linear. Or maybe a linear might fit slightly better than an exponential. Does that make sense? These are both bad, obviously. Whether it's a linear trend line, linear regression line, or an exponential regression model. Both are bad. Is that right? So those data, again, the R squared was 0.05 or 0.04, depending on which model we went with. It says the equation does not fit the data well. So the model does not fit the data well, and the bad fit. And it also states that if you're trying to do predictions, they're not going to be worth anything, essentially. Is that all right? Any questions about these types of things? Okay. So our cutoff for this class between good fit and bad fit is going to be 0.5. And you're going to be asked that. You're going to say, here's the model. Here's the R squared. Is this model a good fit to the data, or is this model a bad fit to the data? All right. And you'll have to pick good fit or bad fit. Any questions about that? Now, next class, we're going to essentially talk about some things to watch out for when you're doing regression. So some things to watch out for, some ways that regression can mislead. But all the calculation parts are done. So if you wanted to, start on the homework, You can start on those homework sections. All the calculation parts are done. Just those last couple of sections are not up yet. Does that work? All right. Well, other than that, I will see you on Thursday.